So why are the underlying arrays of the hash table always a power of 2? When we trigger a resize, why are hash table always doubled like 2, 4, 8, 16, 32? What is the reason behind it? In this 8th video of the hash table internal series, we answer some super cool questions and go in depth on hash table resizing. We understand why we do it, how we do it, why hash tables are always doubled upon resize, why are they always sized as a power of 2, and conclude with understanding how and when we shrink them. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue. Instead, a small focused group of 50-60 engineers every cohort will be brainstorming systems and designing it together. This way, we build a solid system and learn from each other's experiences. The course to date is enrolled by 600 plus engineers spanning 9 cohorts and 10 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The coolest part about the course is the depth we go into and the breadth we cover. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale for any advertisement business. In all, we would cover roughly 28 questions and the detailed curriculum split week by week can be found on the course page which is linked in the description down below. So if you're looking to learn system design from the first principles, you will love this course. I have 2 offerings for you. The first one is the live cohort based course which you see on the left side, and the second one is the recorded course which you can see on the right side. The live cohort based course happens every 2 months and it will go on for 8 weeks, while the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would highly recommend you going for the recorded one. Otherwise, the live cohort is where you can participate and discuss things live with me and the entire cohort and amplify your learnings. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass, and I would highly recommend you to check that out. I put the link of the course in the description down below. So if you are interested to learn system design, go for it. Check out the link in the description down below, and I hope to see you in my next cohort. So in the previous video, we looked at the quantification of performance of a hash table through a factor called load factor, which is represented by alpha, and it is just a fraction of the number of keys that your hash table holds divided by the total number of slots that you have. So if you have a hash table with 50 slots and you have placed 25 keys, your load factor becomes 25 upon 50 is equal to 0.5, right? As load factor increases, your performance would degrade because then it would take longer time for you to find a free slot and place your key there. So which is where, in order to maintain a consistent performance, when your load factor hits a certain threshold, you might want to resize your underlying array, right? So that you can maintain your consistent performance across. So resizing is important, but when do we trigger it? So resizing is a very expensive operation because you have an underlying array in which you are placing your keys. Now you have to resize, which means you have to allocate a bigger array and then move the keys and whatnot. So resizing is an expensive process. So you cannot get either too aggressive or too lenient on it. If you become too aggressive, which means you are very frequently resizing your array, you are wasting a lot of time doing resizing and moving keys here and there, right? If you become too lenient, then you are letting your performance degrade. Right? So there has to be a sweet spot between them. So a very typical strategy that you might see is people trigger resize when alpha is equal to 0.5, which means as soon as your array is half filled, you might want to trigger a resize. This way you maintain a consistent performance. And obviously we can make this logic as complicated as possible, but alpha is equal to 0.5 as a threshold is a very common practice that people observe. Then how do we resize? Resizing is really very simple. It's expensive, but it's simple. So what do? You have an old array of, let's say, size m old, and now you have to resize. Now, which means you have to create a new array of size m new. So what you do? The step goes like this. First step, you create a new array whose length is equal to m new. Then you copy all the elements from your old array into this new array, and then you delete the old array, right? And here, the expensive steps are creating a new array of length mnew is expensive because your operating system would have to find that big of a contiguous memory location and then allocate it. It takes time. And then much more than that, the time would be required for you to copy the elements from your old array to this new array. You cannot just bluntly copy it because hash functions would change. Your keys would be rehashed into this new location. A simple way to do it, you might have heard of a function called realloc. In C language, you can use that to implement it, but that might not be very fruitful because realloc, what realloc does is it creates that new array, copies elements as is. Like for example, if you had an array of length 50, within which you have 25 keys placed, it would literally copy that array as is to this new place, and the later half of the allocation would be empty. That might not be the best strategy for us, given that we are using a hash function. So balancing would be a problem, right? So and the time taken to resize is proportional to the number of keys that you have. So larger the number of keys, the larger time it would take for your OS to allocate it, and larger time it would take for you to copy the old keys and put it into the new. So time to resize is proportional to the number of keys that you are holding. So a typical strategy to resize is always double the array, right? So during insert, if we trigger a resize, we reallocate a new array of 2 times the size and rehash the key. To put it really simple, let's say I have an array of size 4 which holds keys K4, K1, K3 and K2 in this order. And my hash function through which I'm deciding which key goes where is h of k mod m old. So m old is the old size of the array, which means here it would be 4. Now let's say I'm resizing it to 8. So then my hash function would change to h of k mod 8. So I'll have to create first the array of size 8, then iterate through all the keys and find out where they are now placed in the array with h of k mod m new, which is h of k mod n, mod 8. So you'll find the index where you have to place it. So you might see a little, you definitely see that your keys are nearly uniformly distributed and will take up 4 slots out of the 8 slots that are available, right? So because our hash function is changing, you have to rehash all of our existing keys and place it here, right? Now comes a really interesting part. Why do we always double? We have heard it so many times that hash tables, whenever we are triggering resize, we always have to double. Why double? Why can't I just keep growing it one at a time, right? So here when I'm saying double, it is just a growing factor. It is basically called as a growth factor. So here the growth factor is 2, which means I'm always doubling. If my growth factor is 3, I would be always tripling the space, right? So in most common implementation, you would see a growth factor of 2, but it could be 1.2, 1.5, 2, anything. It could be any number, but 2 is a very common implementation. Okay, to understand why we need to do it by 2, let's say we go to the other extreme and say we always increase the array by 1, right? So what we would do is we would allocate a hash table of slot 1, and whenever we add something to it, we would add a new, we would reallocate the array and then insert a new element into that, right? So every time we are just utilizing the entire space of our hash table. Given that, let's see what is the time complexity of this. So I started with hash table of slot 1, right? I inserted a, what I would be doing, I would be allocating an array of size 1 and I would be inserting the element. So number of operations 1. Then let's say I want to insert b into this. So I would do what? I would reallocate. I would allocate an array of size 2. I would copy one element from my previous step because my array had one element. I would copy that one element and then insert b. Total number of operations 2, right? Insert c, when I'm doing it, what I would do is I would first allocate the array of length 3. Then I would copy a and b from my previous step. Then I would insert c into it. The total number of operations would be 3 because 1 for the resize, 2 for copying of element, and 1 for inserting a C. So that is a constant time operation. So that is total number of operations 3. And so on and so forth. If I continue doing it, if let's say I want to insert Z into this scheme, what I would be doing? I would be doing 26 operations. So for n operations, so now overall, if I'm inserting n keys, if I'm inserting n keys in my hash table, the number of operations would be 1 plus 2 plus 3 plus 4 and so on and so forth plus n, right? Because every time you are resizing your array and then you are placing your key in, right? So your hash table will start from 0 with 0 slots. Then you are inserting the first element, it would allocate the array of size 1. Then when you are inserting the second element, it will allocate the size 2, copy and then reshuffle and whatnot. It would do this. So for me to insert n keys, it would require me to do 1 plus 2 plus 3 plus 4 plus up to and so on n operations, which is equal to n into n minus 1 by 2 is equal to order of n square. So if I'm being very aggressive on the resize, where I'm saying that I'll just allocate the bare minimum space that I would need to, my overall time complexity of inserting data into hash table, like inserting n keys in my hash table, would be order of n square. Very expensive, right? So let's say what happens when we double every time. So when I say double every time, what this means that you might start with 1, then when you want to trigger double or you want to trigger a resize, you would make it 2, then 4, then 8, then 16, then 32. Right? You would go that way. So let's say we spot the middle and say that, hey, for me to go from n, let's say my current size is n, and I want to go to 2n. I want to trigger a resize. I want to do a 2n of it, right? But from doing n to 2n, I would have had a situation where I was going from n by 2 to n, because that would be a step back, right? N by 2 to n and n by 2n. We are always doubling. Now let's take a look into when we insert n by 2 elements in the array of size n by 2. Now what would happen, right? I'm taking an example, a very simple assumption that we resize just to make our the explanation simple. We resize when the array is completely filled, right? Obviously, it depends on the load factor that we discussed, that if we would resize it at 0.5, but understanding this becomes very simple when you say that I would resize when I'm completely filling my array, then only I'll resize. So when I'm getting, if my array has 4 slots, when all 4 are complete, then only I'll trigger a resize, right? So this is what we would be doing. Okay, so with this assumption, let's say we insert n by 2 elements in the array of size n by 2, right? So I had n by 2 minus 1 elements at first. I had n by 2, let's say I have slots 4, I'd have 3 slots filled, then I'm inserting 1. As soon as I'm inserting 1, what would happen is I would have to resize, and then basically as soon as my array is filled, I'm basically triggering a resize, right? So I'll be inserting the element and then I'm triggering a resize. So what I'll have is I'm having an n by 2 length array. I'm inserting my final element into it, which completes my n by 2 array, and then I'm triggering a resize. So now my array size would be n, and the state would be, it would have n by 2 elements filled while the other half is empty. Right? So n by 2 elements filled and basically the overall filling percentage is basically 50%. So n by 2 elements filled. Order would not be specific. With illustration, I'm doing it like left half filled and right half empty. But this is just for illustration, making it simple to visualize. Right? But it would contain n by 2 elements filled in the array of size n. Right? And this is where we start. Now, this is the current state. Right? Now let's say we go from n to 2n. For us to go from n to 2n, what needs to be done? To get to the next resize, because we are resizing when my array is completely filled. Right now I have an array of size n where it is filled by n by 2 elements. There is still n by 2 space left. So I'll not be triggering my next resize until I fill the rest n by 2 slots of my array. So for the next n by 2 elements that I'm adding, for next n by 2 minus 1 elements that I'm adding, it would take me order of 1 time to insert. Correct? Because that's what I'm doing. So I'm resizing when my array is completely filled, right? So while inserting the last element, I'm triggering a resize, right? So what would happen is first, for the first n by 2 minus 1 elements, because n by 2 slots are still remaining in my array, right? They're still empty in my array. So first n by 2 minus 1 elements, I can very easily insert with order 1, right? So that is done. And then for the first I've inserted, then when I'm about to insert the final element, I'll see that my array needs a resize because my array would be completely filled. So then what I would do is we would allocate an array of size 2n, right? Would allocate an array of size 2n, copy the elements, copy n by 2 plus n by 2 minus 1. So n by 2 old elements, n by 2 minus 1 newly added n by 2 minus 1 elements into this new array, and then add the final element that we wanted to insert. So now after this what we will have is we'll have an array of size 2n where it is filled by elements n by 2 plus n by 2 minus 1 plus 1. So it will be filled by n elements, right? So this is how your resize, or this is how you'll go from n to 2n. Now let's take a look at the number of operations we would require to do this. So the number of operations would be equal to n by 2 minus 1, because it is taking you order 1 time to insert n by 2 minus 1 elements, because post that only it would trigger a resize. So n by 2 minus 1 you did, then order 1 to insert the final element, right? Plus 2n as part of allocation, because you are resizing the array, it would be 2n operations, plus n to copy elements from your old space into this new space, right? So total number of operations that you are requiring is 7n by 2, which is order n, and which is why we always double. So the total number of operations when we were very aggressively resizing by 1 every time, it was order of n square, n into n minus 1 by 2. When we double, we are getting an order n complexity, which is much better than order n square, right? And this is why we always double. And this does not just hold true when you double, but any time when our growth factor is greater than 1, this would hold true, right? And this is the brilliance of this idea and the core reason why we always double, right? Now let's take a look at another very interesting insight. Why is hash table always allocated as a power of 2? This is again a really common thing to observe. My hash table is always 1, 2, 4, 8, 16, 32 and whatnot, right? Why always power of 2? This is where we would go into the bitwise operator. Like why? Okay, so the underlying array of hash table has length of power of 2. It's very efficient because like the world is doing it, but how? So hash table works on hash functions. So when you want to insert a key, what you do is you take the key, you pass it through the hash function, you get a number, you mod that number by the size of the array to get the index, and then you place the key at that place, right? So here the mod operation is super important because it bounds your integer 32 range into the size of your hash table so that you can place your key at that particular index. But mod function is very expensive. Internally, when you implement the mod function, it does a long division. Maybe it could also do a sign division, but integer division. It does a division, which is a very expensive operation, and then it captures the remainder. Can we do faster, right? And obviously it's all about efficiency at scale, and especially at this micro level, and even a small optimization makes a lot of difference. Okay, so can we do better? So let's see what happens when my m is 4, which means the number of slots in my hash table is 4. Let's see how my keys would change. Like what is the output of my mod function? So if my hash key is 1 mod 4, our answer is 1. So I'll go, so output is 1. That is where I'm placing my key. 2 mod 4 is 2. 3 mod 4 is 3. 4 mod 4 is 0. 5 mod 4 is 1. 6 mod 4 is 2, right? So we see how it cyclically goes from 1, 2, 3, 0, 1, 2, 3, 0 and so on and so forth, right? Can we get this same output? Can we get the same output but without using mod function? That is where the magic of bitwise AND comes in, right? Okay, so instead of doing a mod m, what if we do mod of m minus 1? And this works when m is a power of 2. So we know that m is equal to 4, 4 is equal to 2 raised to power 2, and instead of doing AND with 4, we would do AND with 2 raised to 2 minus 1, which is equal to 3. So let's just take a look at what output it generates. So 1 mod 4 is 1, right? But now, can we get the same output of what 1 mod 4 is with 1 and 3? 4 minus 1, right? So 1 and 3. 1 is 0, 0, 0, 1 and 3 is 0, 0, 1, 1. So when I take an AND of this, I get 0, 0, 0, 1, right? Because 1 is 0, 0, 0, 1, 3 is 0, 0, 1, 1, output is 0, 0, 0, 1, which is 1, which is same as 1 mod 4. Similarly, for 2, it is 0, 0, 1, 0, bitwise AND with 3, which is 0, 0, 1, 1. The output is 0, 0, 1, 0, which is 2. 3 mod 4 is 3, 3 and 3 is 3, right? So 3 mod 4 is 3 and 3 and 3 is 3. So output matches. 4 mod 4 is 0 and 4 and 3, 4 is 0, 1, 0, 0 and 0, 0, 1, 1. 0, 1, 0, 0, 0, 0, 1, 1. The output is 0. 4 mod 4, 0, 4 and 3, 0. Again, it matches. And the final thing where we see the cycle repeating is 5 mod 4. 5 mod 4 is 1. 5 and 3 is 0, 1, 0, 1. 5 is 0, 1, 0, 1. 3 is 0, 0, 1, 1. When we AND, we get 0, 0, 0, 1, which is same as that. But how? How come mod and AND gives the same output? It happens because your AND thing is 2 raised to n minus 1. Because of this, what is happening is your equivalence mod m is equivalent to bitwise AND with m minus 1, where m is a power of 2. Because your AND operation is significantly faster than division, you get a massive performance gain. Massive performance gain, which is why everyone uses hash tables power of 2. So, but why is this happening? Because for a number which is 2 raised to k minus 1, like 3, 7, 15, the lower bits are all 1, higher bits are all 0. And AND operation acts as a filter, right? So the higher bits which are 0, they would always result into 0. The lower bits that are all 1s, they would as is act as a filter. Wherever the 1 is set, it would bring down as is, right? And the numbers are continuously increasing. So this is actually limiting the range that we are generating, because the top zeros or the higher bit zeros that are there, they are limiting your number would not go beyond all the ones that are there. This is such a beautiful piece of optimization, right? So mod function is expensive. We replace it with bitwise AND. When we replace it with bitwise AND, it would only work for the cases where my m, where I'm doing mod m, where m is a power of 2, we would do bitwise AND with m minus 1. So when I'm doing a mod 4 is equivalent to AND 3, or if I'm doing mod 8, it is equivalent to AND 7, right? So 2 raised to k minus 1. This is why hash tables are always a factor of 2, 1, 2, 4, 8, 16, and they are always doubled. And now you know why that happens. Okay. Now we'll, as part of conclusion, what we'll take a look at is we'll take a look at shrinking of a hash table, right? So if the keys are deleted from the hash table, then it does not make sense for us to keep it bloated, right? Let's say if a hash table only has one value and you have allocated 128 slots. It's stupidity, right? You have to reduce it. But when, right? So it does not make sense to bloat that up, to keep that bloated. So we have to shrink it. So we know that we grow our hash table when our load factor reaches half, which means when my array is half filled, that's when we scale up, right? So when should we trigger our shrinking? Let's reverse engineer it. Like, let's go backwards and understand when should we do it. So if your table has n slots, then it would have at max n by 2 elements before we trigger a resize, right? It would have at max n by 2 elements. If your table has n slots, it would have n by 2 elements. Otherwise, it would have triggered a resize, right? So what would be the state? That if it has n by 2 elements, it would have triggered a resize. So number of elements, if let's say I have an array of slot 16, if I have had 8 elements, I would have triggered a resize. So then my array would have been 32. So the max number of elements before we trigger a resize could be 7, right? So when my slots is 16, my number of elements would be 7 at max, because at 8th element we would trigger a resize, right? So if we shrink, let's say if we consider shrinking at this stage, what would happen is we would be shrinking it into half, right? So from 16 we can go to 8, but the number of elements we have are 7. So to fit 7 into this 8 slot, what would happen? This would lead to poor experience, because as soon as we do it, we would again have to trigger a resize, because now my load factor is close to 1, right? So which means that when I have slot 16 and element 7, I cannot trigger a shrink. So let's go a step back, right? So now what does this mean? This means that we need to have enough leeway where, let's say we trigger a resize when we have n by 4 elements, basically n by 4 minus 1. So if I have 16 slots, let's say we trigger it at 3, right? So when we do that, we still get a consistent performance. So when I have 16 slots and I have 3, I'm still getting a consistent performance, but the problem is just one more insert and my threshold would be breached of 0.5 and I would have to trigger a resize. So for example, if we are shrinking from 16 to 8, when my number of elements are 3, from 16 to 8, when my number of elements are 3, just one insert into it, what would happen? My 3 would become 4, load factor would become 0.5, and I would trigger a resize again. So that's a very poor way, right? So we go a step back again. So what we do? So that's where, to keep it very efficient, we need to shrink when the number of elements are such that a few insertions after that would not cause a immediate resize, right? So we go a step even back. So that is where what we do is we would shrink when my number of elements are less than n by 8. So if I have 16 slots, I would trigger a resize when there are 16 by 8 is 2. So basically less than 2 elements when I'll have, that's when I would trigger a resize. Otherwise, you would be constantly doing resize and shrink as we just saw in the example, right? Might be a little confusing. I would recommend loop back into this phase and understand what's happening. Take an example and understand it. Otherwise, this video would be too long. That's why I'm not doing that. But understand the idea behind it. You want to maintain a consistent performance while also ensuring that, hey, just one more insertion would not lead to a resize again. Right? Okay. So this is why, or basically this is when you trigger a shrinking of your hash table to keep your memory utilization pretty efficient. Right? So just to summarize, this has been a long video, but just to summarize, resizing is important to maintain performance. Point number 1. Point number 2, resizing is super costly. Right? We saw how allocate and move keys and whatnot. Third, hash tables is always doubled when we want to grow. In order to maintain consistent performance, order n performance when we are always doubling. Fourth, hash table always has 2 raised to n slots for faster compute because mod can be replaced by bitwise AND. Fifth, you grow the hash table when your load factor hits 0.5, like 1 by 2, right? When your array is half filled, that's when you trigger a resize so that you have enough leeway that you maintain a consistent performance. And you shrink when your load factor becomes 1 by 8. Right? So that again, you maintain a consistent performance without triggering a frequent resize again. And that is it about resizing of hash table. I hope it was amusing. It was fun when I was exploring it. I've always wondered why. And now I finally have the answer for that. So great. I hope you learned something interesting. This was the 8th video in my hash table internal series. If you found this amusing, you'll find this entire series really fascinating. I would highly encourage you to go through all the videos because why not? Yeah, hash tables are such a common piece of data structure that we day in and day out use. We need to understand how they work internally, right? So that's it. That's it for me for this video. If you guys like this video, give this video a massive thumbs up. If you guys like the channel, give this channel a sub. I post 3 in-depth engineering videos every week and I'll see you in the next one. Thanks a ton.